We begin a new unit today, and the unit is called Analysis of Growth. And in particular, in this particular lesson, our first lesson of the unit, we are going to understand how to use growth rates to analyze quantitative mathematical information. So just to kind of get us started, get us thinking, here is this article that tells us the synopsis, the gist of this article is that the graduation rates of athletes in Division I schools is improving. And we could take the time to read this, but according to the NCAA, this is published several years ago, football and men's basketball players are becoming more productive in the classroom. And they give us some information to back that statement up. So they're doing better, which is obviously a good thing. So the purpose of this article, just to kind of fill in our blanks here, the purpose of this article is to highlight the trend. Okay, that's an important key word that we'll be looking at later in this lesson. The trend in graduation rates, and according to this, they are getting better over time, but we're just going to say in general how they change. That's going to be an emphasis of this lesson, is how do we analyze change in a particular quantity over time, whether that's an increase or a decrease over time. So this article presents us with raw information. Okay, it's just in paragraph form. There's a lot of mathematical information contained in it. Sometimes raw information like this can be kind of dry. It can be sometimes overwhelming to kind of capture the full picture. So in this lesson, we're going to be empowered to analyze tables and graphs. Tables and graphs are many times a better way of taking information contained in a narrative and presenting it in a more understandable way. Okay, so we're going to be analyzing tables and graphs critically and really be able to hopefully take them apart from a number standpoint and analyze how the information presented presents a change either in a positive way or in a negative. So our first foundational task here is to really understand what functions are all about, because really what we're going to be dealing with, even though it's raw data, it's going to be in sometimes table form or graph form. We're really talking about functions. So an understanding of what a function is, some terminology involving functions will be very helpful with this lesson as we work our way into more mathematical processes. So what is a function? When one quantity or variable depends on another. All right, so what we're saying here is I'll use the word inputs and outputs because that's going to be key to what we're going to talk about with functions. When I input a number, a quantity into an equation, what comes out of that equation? That's what we're talking about here, when one quantity depends on another. We call the latter of these two, there's two quantities being referenced here. The one that was dependent, you can see the word depends on another. Obviously, we call that the dependent variable. Take care of that. Dependent. And then the former, the first variable, the one that we use to initiate, to plug in, if you will, that's called the independent. We have other ways of referring to these variables. So let's take just some simple examples. you're working a job, and your pay on that job depends on the number of hours that you work. All right, so to know how much you're going to get paid, you need to have a number of hours that have been worked. So the amount that you eventually get paid, the salary or whatever you want to call that, your paycheck, that's going to be the dependent variable. Because we don't know what that amount is unless we have a certain number of hours to plug in and calculate. So the number of hours that you worked is the independent. Try to squeeze that in. Okay, so we also use this phrase to represent this scenario. The amount paid, the amount that you make, is a function of hours worked. Okay, you don't know what you got paid unless you know what the hours worked is. So we start with hours worked. That could be any number. That's independent. But the salary that you make is dependent on that number. Okay, and then I just provided this for context to what we talked about in Algebra 2. This is function notation. F of the quantity hours worked would equal the output of salary paid. Okay, one more example. The income tax that you owe is a function of your taxable income. So in this scenario, the independent variable or the input is your taxable income. How much of your income is subject to income tax? We put that number in, and then we can determine how much you owe with income tax. So that's dependent on your taxable income. So I'll put this as income tax owed. Okay, so just an idea, probably hopefully a review of some terminology, what is a function, and then these words, independent, dependent, input, output, are very important when we're working with functions. All right, another mathematical concept of functions can be illustrated with this function machine. And I think this is a good little visual to help connect a function, and you might call that an equation, with what we call a table of values. How do we generate a table of values from an equation or function? And then how does that relate to the graph of that function? So just a real simple example. Hopefully, again, this is going to be a reminder, a refresher, but let's just take a look. I'm just going to make up an equation here. It'll be a linear equation. So we'll say 3x minus 7. All right. And then I'm going to click OK. Okay. Now, remember, input is what x represents. That's the independent variable. All right, so I can choose any number I want for this. I'm just going to say -3 is my input. All right, when I put in -3, then I'm going to click Run, and you can kind of see this function machine takes -3 as the input, and it gives me -16. The machine basically replaced x with -3 and came out with y. So to use our terminology from the previous slide, x is the independent variable, or the input. Y is the dependent variable, or the output. And then that translates to the graph. Notice how this table of values actually became the graph. So this red dot right here is the point on the graph, -3. Okay, so here's -5. So estimating -3 on the x, and then down on the y, -16. Okay, let's do another one. We'll do another input. Let's do a positive number. We'll say 5. Okay, I put in 5 into the function machine, I input 5, I get an output of 8. So there's the table of values that shows me the dependent or independent and dependent variables. We also use the word domain and range in Algebra 2. And then here's the resulting graph. Input 5, x is 5, output 8, y is 8. Okay, so just simple visual for those of you, maybe it's been a while since you've had algebra, so we're just making a connection here to how functions work, and especially those keywords, independent and dependent, input and output. Okay, so as we move forward, a lot of times we're going to be seeing data presented to us in table form. So when we see data in a table like this, where the data is represented, it's organized in columns, then it's typical, I wouldn't say it's 100%, but it's pretty close. It's typical that the first column is going to be the input or the independent variable or the x value. And then the second column is going to be the dependent variable or the y. So this particular table is a function for height given a certain amount of time in seconds. Okay, it's the function of height given time. And then here's an example of a table of values, but the data is presented in rows. So similar, you can think of, typically, you can think of when this happens, you automatically can know that the first rows go horizontally. The first row will represent the independent variable, or the x, and then the second row will be the dependent, or the y. Okay? All right. So let's take a look at some examples. Here's a table of, this is meant to give us in a particular year, it tells us who won the most, notice this column, the most medals won by a country in a given year. Okay, and these are the years given here. They kind of jump around a little bit. Most of them are separated by 4 because that's when the Olympics are held. So let's identify what the independent variable is. Okay. Let me get my pen back. So the independent variable will be the year. The dependent variable will be the medals won, the most medals won. Just say, shortcut it by a certain country. So what does this mean? What's it tell us? Well, it's, if we fill in the blank, medals won, I'll say most medals won by a country, is a function of the year. So when you're looking at this phrase, the first blank will always be the dependent variable, the output. Output depends on the year. Okay, now let's reverse that. Maybe somebody would say, you would switch these and you would say the independent variable would be the medals won. Well, here's something about functions that we talked about in Algebra 2, and you probably heard this in Algebra 1. When you have an input, to be a function, you cannot have one input. I'll illustrate this with a mapping diagram. We did these in Algebra 2. So here is a proof as to why medals won cannot be the independent variable. So to be a function, when I have an independent variable, it cannot produce more than one dependent variable results. So we use the phrase, a domain value cannot match up to two different ranges. And if you notice, that's what's happening here with, let's just take, for example, 29. 29 metals were won in 1988, and they were also won in 1998. So just a little Algebra 2 review. In mapping diagram form, whenever this happens, when one input produces two different outputs, then this is not a function. So if it doesn't make a function, then we can't make our variables represent dependent and independent as I've done here. But if I take, for example, the year 1988, only maps to one number. There's only one number, and we're looking for the most medals won by a country. Okay, so the year has to be independent because it does not produce more than one value as a y coordinate. Okay, there's example number one. Now, this slide is just to help us understand, and we probably already know this, but sometimes tables are fine, but to really give us a true picture of growth, it's a lot of times more helpful to look at that data in a graph form. And so what's happening here is this table, which represents the population of the United States over a long period of time. There is growth, and we could see that growth with the numbers, but this picture really helps illustrate the magnitude of the growth. That old expression, a picture is worth 1,000 words, that's definitely true. And that's what graphs are for us. They're a picture of quantitative data that help explain what's going on with the data. Okay, so we've talked about functions. What are they? Some key terms relating to functions. Now we're getting into the math behind analysis of change in data. And one type of analysis would be the percentage change of data that's given to us in a function. So the percentage change, it's also known as the relative change, because it's not an absolute. We're breaking it up into smaller chunks typically. Instead of looking at the whole set of data, we're typically just analyzing parts at a time. Relative change in a function is the percentage increase or decrease in a function from one value of the independent variable, that's the x coordinate, to another. And here's the formula, that the Mathies formula, the change in the function divided by the previous function value. I like to use this phrase. You may not recognize it, but you did stuff like this probably in Algebra 1, maybe even in middle school. We're going to take the difference, and I'll illustrate this with our example coming up. I'm going to use it like this: the difference divided by the original. Okay, so let me just illustrate what I mean by this, and then maybe that's a little bit easier to follow than this mathematical sounding function. Okay, so we're going to go back to our data. A lot of our problems are going to use this table of population in the United States, right? So let's just take a look at this table. And example number one says to use this table using the population given, information given on the previous slide, calculate the percentage change in population from 1790 to 1800. Now, the thing about percentage change is the actual calculation only uses the dependent variable. Okay, I know we're looking at the change from one independent variable to another, so we're looking at the change from here to here. That lines up with our definition. But the actual calculation involves the dependent variable, or the y. Okay, so I'm going to look at my table. So in 1790, we had 3.93, and that's in millions. And then in 1800, we had 5.31. So I'm typically going to put the bigger one first because difference means I'm going to subtract. All right, so I found the difference between these. And we have to understand, obviously, looking at the table, we have growth here. All right, if we didn't have growth, then we could have a negative percentage change. But this is going to be growth, so I went ahead and set it up so that the bigger one is first. That's going to make sure I get a positive result. And then the original means the one that, the 1790. Okay, so we grew from here to here, but when I use the word original, I'm talking about the first one. So the 1790 figure will go here. All right, so now we pull out our calculator and we do the simple math. Okay, so 5.31 minus 3.93, that is 1.38. And then we divide by 3.93. And we get the decimal form 0.351145 and so forth. Well, that's why the times 100% is helpful, because we want our answer to be in percent form. So just take that decimal and do times 100 and you get our result, and we're just going to round this to the nearest whole percent. So the percentage change from 1790 to 1800 was 35%, the percentage change in the population. Okay, we'll do another one. Calculate the percentage change from 1800 to 1810. All right, so go back to our table. This is the table that we're working with. So you would have this printed out, hopefully, so you can just flip back. So I'm not going to keep flipping back and forth in my slides. Hopefully you have a printout of this already that you're working from. But that's the table that we're getting our information from. So in 1800, looking at our table, 1800, the population was 5.31 million. We already had that. And from 1800 to 1810, it's 7.29 million. So again, that's going to be growth. So I'll just go ahead so I don't accidentally switch these and think the answer is going to be negative. So it's going to be positive growth. So I do the subtraction and then I divide always by the original. So when I use the word original, I'm talking about the first of these two values. Okay, so once again, go to your calculator, and when you do 7.29 minus 5.31, get your result, and then divide that by 5.31. Doing that myself in my calculator, and I got the decimal 0.372881336, and so I need to it's 7.24. Sorry about that. Numbers are kind of small. 7.24. Let's try that again. 7.24 minus 5.31, and then I divide by 5.31. and I get 0.36346 and so forth. So multiply times 100 to put that in percent form, and that's about 36%. Okay, so a couple examples of percentage change. Those are pretty easy. And now let's talk about average growth rates. Okay, what is the average rate of growth? And I think you're going to find this formula to be very familiar to what you did in the past. The average growth rate, we'll just do a little definition here. The average growth rate of a function over an interval, period of time, is the change in the function. The change in the function you can think of as the y variable, the dependent, the output, divided by the change in the independent variable, or the x. Does that sound familiar? It sounds a lot like rise over run, change in y over change in x. Yeah, this is basically when we were dealing with lines and the average growth rate was consistent all the way across from left to right, from negative infinity to positive infinity, then this is called slope, the slope of a line. But it's basically the same formula. So I'm going to use this terminology because this is very popular in college math classes. I'm going to say that delta y over delta x. Delta, that Greek letter delta in math, means the change in the y values divided by the change in the x values. Or you could go back and use y2 minus y1, x2 minus x1. Okay, so let's do a couple of examples of those. Calculate the average growth rate in the U.S. from 1940 to 1950. All right, we're using that same table. So it really doesn't matter which one of these you treat as y2, y1, x2, x1. You just need to be consistent. So let's go to our table and look up 1940, and that's 132.16. So y is the output. Okay, so I'm going to take 132.16, that's the output population, the y, or the independent variable. And then for 1950, that's 151.33. Well, here it's very important that you stay consistent. So the independent variables are the years. So since 132.16 was listed first, that represents 1940. And this represents 1950. So that is very important that you stay consistent. If you cross these up, then it's going to change the sign. And you can have negative growth. So you just want to be careful that you're consistent. All right, so let's do some math. So go to our calculator, 132.16, and subtract 151.33. And that's negative 19.17. And then down here, obviously, that's going to be negative 10. And then let's do the division by negative 10. And we get 1.917 as our average growth rate. I'll just go ahead and say 1.92 million. There's in millions. So what does this mean? Well, I want you to use words to, whenever you're asked this question, what is the meaning of this number? So the population, this is growth rate, population of the U.S. grew on average, okay, on average, by 1.92 million per year. Okay, so this is a yearly average that we've done. Notice we divided by essentially 10. It was a 10-year period. So this is the way you would word something to that effect, what the meaning of the average growth rate is. Make sure you indicate what the unit meaning here per year, that's important. And then just wording like this helps me know that you understand the context of the problem. So get into the habit of not just spitting out numbers, but we want you to make sense of the numbers. So I want you to be good at complete sentences, explaining what these numbers actually mean in the context of the problem. All right, let's do another one. Show that the average growth rate from 50 to 60 is 2.8 million people per year. All right, so going back to our table, if you want to go back and look at that, in 1950, the population was 151.33 million. And then in 1960, it's 179.32 million. So those are the dependent or the outputs, and divide by the independent or the inputs. Those are the years. And now we go to our calculator and we subtract, divide by -10. And sure enough, now we're going to get 2.79, but in rounded form, that's going to be 2.8 million. All right, so we're just basically using the formula to verify that this is accurate, and that checks. Now go through your process of explaining the meaning. So much like we did here, the population of the United States, I should have said up here, and I didn't. I need to include between 1940 and 1950 to include that as well. And same thing here. So population of the U.S. grew on average by 2.8 million people per year between 1950 and 1960. All right. Very good. Okay, a couple other math concepts to cover, and then we'll be done. We'll be ready to practice. Interpolation. The process of estimating unknown values between known values, data points, using what we just learned, the average growth rate. All right, let me show you an example. In 2007, 38.2% of college freshmen believed that the economy was headed in the wrong direction. In 2011, that figure became 49.1. So there's an increase, there's growth in that belief that the economy was going in the wrong direction. So using these figures, we want to estimate the percentage in the fall of 2008. So we're not given that in our information. That's why this is called unknown. But we're going to make an estimate based on the average growth rate. All right, so let's figure out what the average growth rate is. So we can do this either way, 38.2% minus 49.1%. Okay, those are the outputs, percentages. And then the inputs are typically going to be years. And just make sure you stay consistent. So 38.2 is the 2007 year, and 49.1 is the 2011. All right. So let's go to our calculator, and this comes out to be 2.725 per year. That's our average growth rate. So we're growing at positive 2.725% per year. So using that number, it's pretty simple. If in 2007, 38.2% believed that the economy was tanking, then all we have to do is take the 2007 number and add one of those years that we came up with our average growth rate. And when we add these together, we'll have our answer. So adding these together and just rounding to the nearest 10, we get 40.9%. Now that's an estimate based on the average growth rate between those 2 years. Morning. All right, we'll do another example. What about in the fall of 2009? Well, pretty simple. We just, again, take our 2007 and we're going to add 2 of those. Or if you want to do this number times 2, that's okay as well. And after you've added those together, you'll have your result, which is 43.7%. And again, that's an estimate based on where we know that 38.2% was an actual number, but we aren't given any information about 2009. So, all right, here's another interpolation example. We have this, according to this website, it gives us information about the national debt of the U.S., pretty hot topic in every election cycle. But as of November the 12th of 2013, it's grown quite a bit since then. It was 17, they expressed this as 17 million. This is 17,162,410 million. Whenever you have a million, that's another way of saying $1 trillion. So we could just say this as $17 trillion. Okay, that was as of November the 12th. It also tells us that it continued to increase at an average of 2,690 million per day since the 30th of September 2012. So that was consistent growth, mostly because of interest per day. So use this information to estimate the national debt as of November the 30th, 2013, 18 days after November the 12th. All right, so we start with our $17 trillion number as of November the 12th. And this is pretty basic. On November the 30th, that's obviously 18 days. So we just take this per day growth amount and multiply it times 18. So 2690 times 18 is 48,420. Now that's in millions. And then we just add these together. So it's still over 17 trillion, but it's obviously a little bit higher. 17 trillion, 210 million. Sorry, 17 trillion, 210 billion, 830 million dollars. And so this is, and you can just state this in terms of million. All right, there's your answer for example number 2. So those are some interpolation examples where we're interested in coming up with estimates of data in between given data. And then we have extrapolation where the difference here in inter, the prefix inter means between, extra means outside of or beyond. So that's what extrapolation is. It's similar in that we still use the average growth rate, but instead of having information that we're going to find between 2 given data points, we are going to go beyond, which is going to enable us to forecast a little bit. So the process of estimating still. Unknown values beyond the limits of available data using the average growth rate, just like interpolation. But this is going to enable us to forecast trends. All right, so let's do a couple examples. There's an epidemic. There's an average of 12 new cases per day. We have a total of 500 as of today. So what do we expect to have 3 days from now? Pretty basic. We take 500 and 12 per day for 3 days. 12 times 3 is 36. So we can forecast, according to this, that we estimate we're going to have 536 cases 3 days from today. All right, similar here, we have an epidemic, 13 per day. We have 200 as of today. How many can we expect? This should be 4 days from now. So 200, and so 13 times 4 is 52. Pretty easy. We should expect 252 cases total 4 days from now. All right, so that is it for your examples. You're now ready to practice, and I've given you the problems that need to be practiced that relate to this lesson. So if you have any questions about those, let me know. I'll see you next time. We're just going to estimate that based on the annual rate of growth.